Ok, então bem-vindo todos e todas ao nosso seminário Fique em Casa de Geometria Algébrica. Eu vou pedir para que todos desliguem o microfone enquanto não forem fazer uma pergunta, né, para evitar interferência. Então, vou apresentar agora o nosso palestrante dessa semana, o Lucas das Dores, que começou remotamente um pós-doc no IMPA agora esse mês, né, então oficialmente é do IMPA. E ele vai falar para a gente sobre schemes of rational curves on del Pezzo surfaces. Lucas, por favor.
Thank you. And first, I'd like to thank the organizers to give me this opportunity to speak about what I've been working on my thesis. And the way I like to think about scheme of rational curves of the Pezzo surface. First, I should start saying that the schemes we're actually going to look at are schemes parametrizing morphisms from the projective line to the Pezzo surfaces. So not to say I'm not warning you before, it's a bit different than schemes of rational curves themselves, but they contain all the information we need. The way I'm going to talk about those is on a sliding scale of generality. First, we're going to speak a little bit about general properties of schemes parametrizing morphisms, and then properties of schemes parametrizing rational curves for morphisms in blowups, on blowups, and then on blowups of the projective space of points, and then finally the Pezzo surfaces. We are going to get to that slowly. So to begin, we should start first by fixing some notation and conventions. So during this talk, we are going to be working over a ground field K, which is algebraically closed. X will usually denote a quasi-projective variety or a quasi-projective scheme, say, over K. And more P1 to X is going to denote the scheme parametrizing morphisms from P1 to X. These schemes usually have countably many components, not finitely many, and they are very central in many areas of algebraic geometry, and they have a central role in classification of birational geometry of Fano varieties. A lot is known about their local behavior with deformation theory of Hilbert schemes and so on. But as I said, they have countably many irreducible components, and describing them globally is not that easy. Finding, for instance, equations for the irreducible components and projective spaces, this is not that straightforward. However, if X is just the projective space, we do have a nice description. That is, if we have X, the projective space, and dimensional projective space, then we know that the scheme more P1 to Pn, it's just a disjoint union of closed subschemes, which I'll call more D, P1, Pn, parametrizing morphisms of degree D. And with morphisms of degree D, what I mean is that the morphisms from P1 to Pn are given by homogeneous polynomials of a given degree, and this is going to be the degree D that we're talking about. And the way to understand this more D is just as an open subspace, an open subscheme of the projective space whose coordinates are just the coefficients of the polynomials defining the morphisms. So as an open subscheme of a projective space, you already know quite a lot. You know, it is going to be irreducible, it's going to be non-singular, and it's going to have the dimension the same as the projective space it's embedded on. And in this case, it's n plus 1 times d plus 1 minus 1. And that's for each d on the natural number. So we actually have a nice global description of the scheme more P1, Pn here. Moreover, if we have an X, a closed subscheme of Pn, we can realize more P1X as a closed subscheme of more P1 Pn. And the classical way to do that is, suppose we have equations for X. Then these equations will induce closed conditions on this projective space, on the projective spaces whose coordinates are the coefficients of the polynomials defining the morphisms. So for each d, we can realize more d P1X as a closed subscheme of more d P1 Pn. And in total, we are going to have a closed immersion of more P1X on more P1 Pn. But we actually have a more general situation. We don't need to have morphisms between these schemes, parametrizing morphisms. We don't need just a closed immersion. Actually, any kind of morphism induces a morphism between schemes of morphisms. Say X to Y, we are going to any morphism from P1 to X. If we compose with a morphism to Y, we are going to define a point on more P1 Y. What I want to say is the following. We actually have a functor, which I'll call more P1 dash, on quasi-projective schemes over K to the local unitarian schemes over K. Just taking any X to the scheme parametrizing morphisms from P1 to X. They are going to respect file compositions and isomorphisms. And this will be a useful way of seeing this. There is plenty of application of that, as we will see in a second. So, and this gives rise to questions, of course. Suppose that we have just a morphism from X to Y, quasi-projective varieties or quasi-projective schemes. So what properties from the induced morphism Fm between spaces parameterizing morphisms can we deduce from the properties of F? Well, at least we have a hint here above that this, if F is just a closed immersion, maybe this induced morphism should also be a closed immersion. And maybe this is also true for open immersions. And maybe we can also deduce some other kinds of properties of that. It's a rather naive question, because of course these schemes parametrizing morphisms are very sensitive to the geometries of X and Y. So an absolutely general morphism, we will have little hope that we can deduce a lot on the induced morphism. But we do have the following. And a small lemma. This functor more dash preserves open embeddings, closed embeddings, and fiber products in the following sense. If we have more P1 the product, it's just isomorphic to the product of the schemes of morphisms. Only these three properties are already give us plenty of room to play and a lot of tools to deduce further properties. But what if F is not, F morphism from X to Y is not as well behaved as open and closed embeddings? As I said, if it's too general, I think we have little hope of deducing anything very deep, very general, because it's all very, very dependent on the geometries. But suppose that you have, for instance, a birational morphism. we have at least that this birational morphism is an isomorphism in between open subsets of X and Y. And maybe we can use that information to deduce something. For instance, suppose that we know the global behavior of the target scheme of morphisms. Can we deduce something about the source and vice versa, of course? Well, the first step of looking at birational morphisms is, of course, looking at blowups. And that's what we're going to try to do now. We're going to try to describe some properties of morphisms from the schemes of morphisms from P1 to blowups by this induced morphism. So let's get to it. Take Z, a closed subscheme of a projective scheme X, and consider sigma the blowup of X along Z, just like so. As I just remarked before, and as it's very well known, we have an isomorphism between open subsets U, which is the complement of Z, and V, which is just the preimage of U under the blowup. So that we have this very nice diagram on the left. And if you want to guess, we defined this functorial approach so that we can actually just apply functors to our diagrams. So if we just apply the Morp1 functor defined just before, what we get is a commutative diagram like so. We have the induced morphism of the blowup, and we know that the horizontal arrows are just open embeddings by the preservation of open embeddings, and this vertical arrow is an isomorphism. What I'm saying is that these schemes of morphisms here have open subsets in common. Now, the nature of these open subsets here, it's again highly dependent on the nature of these open subsets inside our original varieties or schemes. And they can be very large or very small. They can miss entire components here. Since they have uncountably many, these open subsets can be small. But still, it's useful to know that they are here, and they are going to be useful later on as well. So what is this, this subscheme here? It's just morphisms whose images are entirely contained, morphisms from P1 whose images are entirely contained on U in this open subset. Okay, we have a good control on that now. What happens if the image is not entirely contained in U? That is, the image intersects Z, the closed subscheme that we are blowing up, but it's not entirely contained in Z. Let's have a look at that. So we're considering the same situation. And suppose that we have a morphism from P1 to X intersecting the open, the complement of Z, non-trivially. It can be entirely contained in Z or just intersecting Z. So we actually have that this will induce, since this is going to be, the blowup is going to be an isomorphism on open subsets between these two, we are going to be able to lift this via a rational map. There will be a rational map lifting F. But recall that P1 is a non-singular projective curve. So rational maps naturally extend to morphisms, actually. So instead of just having a rational map, we actually have a unique morphism making this diagram unique. And this can be translated in terms of these schemes of morphisms in the following way. So lemma, let sigma m be the morphism induced by the blow-up sigma, and consider n to be the open subscheme on morph1x consisting of morphisms whose image is not entirely contained on the closed subset Z. And let n prime be the preimage of this n. Then the restriction of sigma m to this n prime is a bijection on k points. That's what we had just seen. In particular, this morphism is locally quasi-finite. Locally quasi-finite because, well, again, we can have countably many components here. So it's not going to be quasi-complex necessarily. So maybe I should slow down. Are there any questions so far? Okay. So let's try to give some, at least some topological intuition about what's happening here. So since this restriction is bijective on closed points, since we're working with k algebraically closed, k points are just closed points. It's going to be in particular injective as morphisms of topological spaces, as on the underlying topological spaces. So you can see I'm representing this on this very professional looking diagram. Suppose that we can take an irreducible component on n and let n0 prime be just the preimage of this component. And we have this injection of topological spaces. We cannot guarantee that the preimage of this n0 is actually irreducible. Of course, all the closed points of here go to closed points of that, but it might happen that what we have is actually something a little bit more like this. We have pieces. I have several pieces just covering the closed points of n0. And I want to make another observation here. Suppose that this n0 intersects the open locus of morph1x, which consists of morphism whose image is on the complement. We know by this here that we have an isomorphism between these U, which is the complement of Z, and some open subset in morph1 to the blow-up. So what we have here is that this is an irreducible component, so this is going to be, it doesn't look like this, but I swear it's an open dense here. So there will be one component here, which will also have an open dense isomorphic to an open dense on n0. And we will conclude that the other small pieces are going to be of less dimension, or that's the intuition we are going to have. Okay. Now let's go to examples. Let's try to specialize a little bit again. So what we want now is to be able to use this description to n as big as possible. And therefore, what we need to do is to shrink this morph1z as much as possible. And let's do that by just taking an example when X is just the projective space and Z is a point. And see if we can work things out from this. Okay, let's consider this example then. X is Pn, Z is a point, say 1, 0, 0, 0 in Pn. we have this nice fiber diagram here, where E is just the exceptional divisor of the blowup, sigma is the blowup. And now consider the following. Let's just notice that more P1 to a single point, it's just also a point F0. That is a morphism which takes everything in P1 to a close point. It's a constant morphism. So when we apply the morphism, the more P1 functor to this diagram here, we have obtained this fiber diagram right here. Remember that the more P1 functor preserves fiber products. So this here is, it's also fibered. Well, what does this mean? It means that the fiber of this single point, which is just a constant on more P1 Pn, is the whole more P1 to the exceptional locus. It's not surprising. We contract the exceptional locus under the blowup, and we have this closed subscheme here, which is just contracted to a point here. But what we obtain out of that? We obtain that n on the previous lemma, it's just more P1 Pn minus a single point. So all the rest here, if we take a single point, all the rest here is locally quasi-finite and a bijection in K points. And we are going to see a lot of this splitting behavior that I commented a slide ago. So to see this splitting behavior, we can consider the following. We can go back and consider a classical construction of the blowup. So considering the same situation, we know that we have the following diagram. We can embed the blowup on the product of the projective space Tn and Tn minus 1. And then the blowup is nothing but the composition of this closed immersion and the projection to Tn. And we also obtain an auxiliary morphism, which comes from the projection to Tn minus 1, which I'll call tau here. And well, now that you've seen a commutative diagram, and if you're like me, you want to apply the functor on that as well. So what we will have here is, sorry for the sudden change of shape, but it didn't fit otherwise. Instead of a Cartesian square here, we have a Cartesian parallelogram. And what we have is we're going to have the induced morphism sigma m, an induced morphism tau m, and a closed embedding of more P1 to the blowup into the product of this scheme's parametrizing morphisms to Pn and to Pn minus 1. And now we have actually two morphisms to use to try to obtain some splitting of more P1 to the blowup. And that's what we're going to do. But before doing so, let me introduce a naive definition, which is going to be useful for this, which I call parametric multiplicity for the lack of a better name. Maybe it's already named somehow. And if you guys know it, let me know. Okay, so consider a non-constant morphism from P1 to Pn. As I commented before, this is given by homogeneous polynomials of a given degree d with no factors in common. And now, suppose that we have this point 1, 0, 0, 0. Then we know that P is on the image of this morphism, if and only if f1 to fn vanish at this point, at 0. And this will happen if and only if there is a homogeneous polynomial, h, that divides f1 to fn, not f0 in this case. And I will define then the parametric multiplicity of f at p to be the maximum of the degrees of h, such that h divides this, as h divides the polynomials f1 to fn. And if the characteristic of our base field is 0 and f is birational onto its image, this parametric multiplicity will just coincide with the multiplicity of the curve given by this scheme theoretic image of this morphism f. If the f is not birational onto its image, then it's probably going to be a cover of this curve, and then this parametric multiplicity will just be the multiple or the multiplicity times the amount of times you cover. If yet the characteristic of your base field is positive, then we might also have Frobenius endomorphism in this, and this parametric multiplicity will also be sensitive to Frobenius endomorphisms, and it's going to be multiplied by powers of the characteristic of our base field. And okay, now we have this naive definition, which is going to be very useful for us in a moment. Let's go back to our, well, maybe again, I'm just babbling on if anyone has any questions so far. Okay, so moving back to the example of the blow-up at a point, let's consider any point in more P1 to the blow-up outside of, whose image is outside of the exceptional divisor. Okay, so sigma m of this point G, that is this G in between brackets, it's the point corresponding to a morphism G from P1 to the blow-up. This corresponds just to the point, this is the point corresponding to the composition. That's how these auxiliary morphisms actually act. So this is going to belong to some more D for some D bigger or equal than 0. Of course, we know already the description of more P1 Pn. It needs to end up on some irreducible component. And moreover, with the description, with a naive description of the blow-up and the equations of the blow-up inside Pn times Pn minus 1, we actually see that the point tau m, which consists of G composed of tau, belongs to some more E, also belongs to some reducible component, more P1 Pn minus 1, for some E less or equal than D. In this case, it will happen that the parametric multiplicity of this composition, G composed with sigma, is exactly D minus E. And we'll call this, we'll define this to be M. Very good. And finally, we'll define this MDM to be the preimage by a sigma M of more D P1 Pn intersecting with the preimage of tau M more D minus 1 P1 Pn, Pn minus 1. This is a lot of symbols. I know it's a bit heavy. I'll put this in a Cartesian diagram in 30 seconds time. so that maybe the visualization is a bit less bulky. But I want you to notice just one thing before. If m is equal to 0, that is, if this parametric multiplicity is actually equal to 0, then this md0 is going to be isomorphic to more d p1 to pn to the complement of pn to the complement of p in pn. And that's exactly because we are avoiding the blown up point, the points that we are blowing up here if the parametric multiplicity is equal to 0. So this is exactly on this open subscheme that they have in common in more d p1 pn. Therefore, this guy here, md0, is going to be irreducible of dimension n plus 1, b plus 1 minus 1. Okay, so as I promised, let me give you just a pictorial description of this pictorial. Diagrammatic description. So we have here the auxiliary morphism, more p1. To blow up, we have sigma m and have tau m. We take the reducible components, more d, p1 pn, and more d minus m, p1 pn minus m. Take the scheme theoretic pre-images, that is just a fiber product here of each. Then do it again. Take the fiber product of this over this guy here. And we obtain this MVM. Okay. Now, actually, it might not seem like it, but we already got pretty far. We already can describe the scheme of morphisms from P1 to the blow-up as a scheme of constants, of course, of more P1 to the blow-up. Also, the non-constant morphisms from P1 to the exceptional divisor. And we have, for each D, we have MDMs for every M smaller or equal than D. And we have this disjoint union. This is all disjoint. Indeed, it is disjoint. They cannot have common points because each MDM is going to project to specific irreducible components. And if the D and M are different, they're going to project different components on more P1 Pn and more P1 n minus 1. So we actually have a disjoint union here. And this is exactly the topological intuition we had before. So this is more D P1 Pn. And if we take the pre-image via sigma m, what we have is a splitting. And we have this splitting according to these parametric multiplicities here. Moreover, more P1 Pn minus P intersects this. So we have an open subset here, which is isomorphic exactly to this MD0, as I commented before. And for the rest, we have smaller pieces. This gives us a nice description of more from P1 to the blow-up, at least in terms of partitions, right? In terms of, we have some partition of this. In fact, if we use this case carefully, we can generalize this for an arbitrary collection of points. And this is precisely the content of the next theorem. So let P1 to PR be a finite collection of points in Pn. Sigma be the blow-up of Pn along these points with an exceptional divisor E. And let M be now a multi-index, M1 to MR, an R tuple of non-negative integers. Then we have a partition of this blow-up, more P1x, as a component of constants, a component of non-constant morphisms to the exceptional divisor, which we already know are going to be fibers of just points in more P1 Pn, and this disjoint union of MD M bold for each MI is going to be less or equal than D. And the description of this MD M bold is the following: a K point G belongs to MDM if and only if the degree of the composition of G with sigma is D, and the parametric multiplicity of this composition at Pi is exactly Mi for all I. Moreover, if all of the MIs are 0, and the 0 are irreducible of dimension n plus 1, d plus 1 minus 1 for each d. Very good. Now, I should give a warning, although we have a nice partition, and I didn't require anything special from the points, the collection of points, except that it is finite. Even though we have this partition, it might be that some of these MDMs are empty. For instance, consider R equal to 3, that is, we have 3 points, and suppose they are non-collinear in P2. So, of course, M1, 1, 1, 1 is empty because we are not going to be able to project to a line into 3 non-collinear points, passing through 3 non-collinear points. Okay. Before addressing the issue whether these MDMs are empty or not, or which of them are, let me start talking about what I promised to talk about in the beginning of the talk, the Pezzo synthesis, because now we do have enough tools to talk about it. So, coming back to this, we see that now we have a partition of the scheme of morphisms from P1 to the blow-up, to blow-ups of Pn at finitely many points. Notice, however, that this partition does not depend on any embedding of X into any projective space. We are not talking about the degree of these morphisms from P1 to X. So this is some other information we can actually add. So we can try to refine this according to their degrees and try to find which MDMs are on which degrees. And that's precisely what we can do with the Pezzo synthesis, since we have such nice candidates for an embedding in Pn, which are the anti-canonical embeddings. And it will follow, this will follow. So let R be a positive integer, which is less or equal than 8. And let sigma be the blow-up of P2 in R points in general position. And then we say the exceptional divisor is D. And we will denote M bold again to be a collection of non-negative integers, and the absolute value of M just to be the sum of each Mi. And now let A be a positive integer such that A times the anti-canonical class is very ample. We know that, of course, we know this. If R is up to 8, we have that the canonical class is ample, therefore we have a multiple which is very ample. And the corresponding embedding yields the following partition. So we can determine which are the morphisms of degree E from P1 to this blow-up. And they are going to be given by morphisms of degree E from P1 to the exceptional divisors and to all the MDMs satisfying this numerical condition. 3D minus the sum of mi times a needs to be equal to e. That's for each integer e, of course. So we have a natural refinement of the partition in terms of degrees for the Pezzo surfaces, which are given by blow-ups of points in general position. Okay, so one of the last things I would like to try to comment with you now is, suppose that we know that each of these MDMs is non-empty. Are there any numerical criterions so that the dimension of MDM depend on D and M? Again, it will also depend a lot on the configuration of the points, but if we assume that points are in general position, maybe we can do so. Or maybe it doesn't depend at all. It's worth asking that, and I will provide a partial answer at least. This is the content of the next theorem. So for this one, we need to suppose that the characteristic of the field is actually 0. Let sigma be the blow-up of P2 at R points in general position. Suppose there exists a rational curve of degree D in P2 passing through these points with multiplicities, with given multiplicities, M1 to MR. And suppose also that its strict transform under sigma is non-singular. That is, when we blow up, we resolve the singularities of this curve, of this rational curve. And then denote M both to be exactly the multi-index with those multiplicities. Then there exists a unique reducible component, MD0, MDM0 in MDM, such that the dimension of MDM0 is the maximum of d squared plus 1 minus the sum of the square of the multiplicities and 0 plus 3. And let me spend a few minutes giving the idea of the proof of this, so that at least this 3 is obvious where it comes from. So first, let's take C to be a curve satisfying the conditions of the statement, a rational curve passing through points in general position with specified multiplicities, which is resolved by the blow-up of these points. And consider the following. For each positive integer D, we consider a morphism from more D P1 P2 to this projective space, which is nothing but the complete linear system of divisors of degree D in P2. And acting on K points, just as following, you take F and you take the proper push forward of P1. This is going to be a divisor on P2. So this morphism psi D is invariant to the natural action we have of the automorphisms of P1 in more D P1 P2. That is, we just take F and compose with any automorphism. This is going to describe the action. And each fiber of this psi D is irreducible of dimension 3. Next, we have to prove that the image of this composition of psi D and sigma M restricted to MDM dense on a sublinear system of this one, of the complete linear system of curves of degree D, containing C. And finally, we use a result of Mel and Hernandez, which actually gives us the dimension of such linear systems. Since this curve is resolved by the blowing up of these points, actually the dimension of this is going to be the maximum of the self-intersection of the strict transform plus 1, or its strict transform plus 1 and 0. And this is exactly where this, this number comes from. Finally, we use the theorem of dimension of fibers and for this composition so that we can actually find a unique reducible component on MDM. And this is, of course, everything needs to be checked that it actually works this way very carefully, but this is an outline of what has to be used. Okay, so now, the last few slides, there is a very natural question, which is, okay, I suppose that I have a nice curve which satisfies some conditions that give me that I actually have non-empty MDM with such and such dimension. But when do we actually have that these curves exist? This is a quite non-trivial question of enumerative geometry. And luckily, I don't have to answer that straightforwardly. Someone did that for me. So there is a classification by Gimigliano, Harborn, and Ida that they give a complete list of rational curves passing through points in general position, which are resolved by blowing up these points via their degrees and the multiplicities, that for are up to 7, of course. Well, not of course, but that's what we have so far. And then, thanks to this, it follows that we can actually find a nice list of these components of type MDM0 for the Pezzo surfaces of degree greater or equal than 2. We can also count them because there's a finite amount of those, and determine their dimension via the formula we had on the previous theorem. To illustrate that, I will just show what happens up to degree 3 into a smooth cubic in P3, which is the Pezzo surface. It's just the blow up of P2 and 6 points in general position. And we can actually find a nice table here. Of course, it doesn't end at degree 3. We can go on, and actually there is an actual more complete table in my thesis, but it doesn't fit here. So we look at degree up to 3, and that actually gives some agrees with some classical descriptions we have, that curves of degree 1, that is lines passing through 2 blown up points, when we take the strict transform of those under the blow up, they are going to be lines in the cubic. The same is going to be with conics passing through 5 points. And they are also going to be, the strict transform is going to be a line. The other lines are the exceptional divisors, so they are not of type MDM0. So they are not in this table. And this I have the type of the M, but of course, this is up to permutation of these indexes here. So we can actually count the numbers of this MDM0 by just counting the number of permutations of the multiplicities here on this tuple. And just computing the dimension with the formula we have, we obtain that. The same agrees here, for instance, for of curves of degree 3. We know that curves lines avoiding all the blown up points, when we do the strict transform of those, they're going to be cubics. And we obtain then that degree in P3 is going to be 3. And so on. We can keep increasing this and just counting for every degree. Of course, there is a more concise combinatorial description to give all of these quantities and dimensions, but this guarantees that we have plenty of cases that we can find non-trivial MDM zeros for given the MM. And I think I'll stop here and thank you all for your attention.
Okay, I think we can thank Lucas. Are there questions for Lucas?
I have a question.
Sure.
How does the stratification of morphisms to Del Pezzos, I mean, how does it compare to what you would get if you imagine using a presentation of morphisms in terms of Cox coordinates for the Del Pezzo surface?
Sorry, in terms of?
In terms of Cox coordinates for the Del Pezzo surface?
I have not thought about the Cox coordinates of Del Pezzo surfaces, so unfortunately I can't tell you how this stratification would look like.
Okay.
So I have another question.
Sure.
How do you connect these to the moduli of stable maps?
That's yet another thing. That's yet another thing that people keep asking me, how to connect this with the moduli of stable maps. I'm still not absolutely sure if when I take this closure and the moduli of stable maps, if they are going to be still disjoint or what is going to happen to this stratification. I am not sure, but this is something I still have to think about.
Because when a rational curve of a certain degree degenerates, it splits, it breaks up, right? Mm-hmm. So you're going to have rational curves of a smaller degree. So it seems that, I don't know, maybe you could use these to find to give a stratification for the moduli of stable maps.
Possibly, this.
Like, yeah, you go to the boundary and then a map of degree D, say decomposed in two maps of degree D1 and D2 summing up to D.
Mm-hmm, mm-hmm.
And then if you characterize them, maybe you can get a description of the stratification. But then you have these conditions here, right, of the multiplicities that you impose. That I haven't seen being imposed for stable maps, so I don't know exactly.
Yeah, yeah, yeah. I'm also not sure how that would look like on stable maps, but that's definitely something worth thinking about.
I think that this MDMs for different multiplicities, I think they will appear in the boundary when you take stable map, because you have say a curve of degree D, a generic curve of degree D. When you look at this strict transform, and when it will degenerate to something that when downstairs it acquires a multiplicity of at the point, upstairs it will appear in one of the MDMs, and you have some vertical components. So I would guess that they are connected in this way, but I don't know. But Lucas, I have sorry, there is a lot of noise here. But I want to ask you something in this theorem that is on the screen. So you compute this dimension, but there is also the expected dimension that is computed using the anti-canonical degree. So does this proof also give you that these components are generically reduced? I mean,
no, this does not give me that. In fact, to prove the theorem, I take reductions of them all the time. So I only actually get the topological component of this. I'm not sure they are generically reduced or reduced whatsoever. It might very well be that there is some reduction involved in general, but I really just look at the topological data here. I did not keep track of the scheme theoretic data.
Are there more questions? So if not, let's thank Lucas again.